Hello, this is FlippedHarber for Precalculus. In this video we're going to cover section 7.5, simple harmonic motion and damped motion. Our objectives for this lesson are to find an equation for an object in simple harmonic motion, analyze simple harmonic motion, that means they'll give us an equation and we need to talk about it, and analyze an object in damped motion. The outline for this video will talk about what simple harmonic motion is. We'll give a simple theorem about harmonic motion. We'll talk about the frequency of harmonic motion. We'll talk about how to find the equation for an object in simple harmonic motion. We'll talk about analyzing the simple harmonic motion of an object. We'll talk about damped motion, and then analyzing a damped vibration curve. So simple harmonic motion is quite simply an object that is vibrating back and forth. An example of this would be a tuning fork, the pendulum on a clock, or an oscillating spring. Now an oscillating spring can actually exist in a couple different ways. There's springs that bounce up and down. There's also what's referred to as a torsion spring, where it spins back and forth. And they actually use those in some clocks. Here's our theorem for simple harmonic motion. Quite simply, they just give us a couple basic equations that we're going to try to fit harmonic motion to. An object in simple harmonic motion can be modeled with either a cosine or a sine function. So we've got these two possible equations that we're going to try to fit to simple harmonic motion. We either say that d, the distance from the rest position, is equal to alpha cosine of omega t. So that cosine is operating on omega times t, not just the omega there. Or d is equal to alpha sine of omega t. Now again, d is the distance from the rest position, the origin. Where would the pendulum, the tuning fork, or the spring be if it was not vibrating? Alpha and omega are constant values that we need to figure out. That alpha is our amplitude, and then 2 pi divided by omega is the period. The period is the time that it takes for one full oscillation, one full back and forth motion. Now, which do you choose, cosine or sine? Well, that's basically decided by what are they describing as the starting position. If the object at time equals 0 is at a distance 0, then we use the sine function. If they're saying that the object starts at some extreme side of its oscillation at time equals 0, that's when we use the cosine function. So whether we use the cosine or the sine equation depends on where the object is at time equals 0. Now our frequency is 1 over the period. It's the reciprocal of the period. It's equal to omega over 2 pi. So they'll talk about, this object has a certain frequency. Well, basically what we want to do is find omega from that. It's the number of times that it oscillates in 1 second. Now, you can have frequencies that are big numbers. You can have things that vibrate several times in a second. Or you can have frequencies that are rather small, where it might take several seconds for it to oscillate once. So that means our frequency is a decimal or a fraction. So when they want us to find the equation of an object in simple harmonic motion, they will tell us some information to try to give us ways to find the alpha and the omega for our equation. And they'll try to tell us some information to basically make the decision, is it a cosine equation or is it a sine equation? So here's an example of one. An object attached to a coiled spring is pulled down 4 inches from its rest position and then released. So right there, they're telling us some information with this 4 inches, and they're also telling us that it's released away from its rest position. So that actually tells me which equation to use. The time for one oscillation is 3 seconds. So that 3 seconds is important. What is it though? We'll talk about that. So obviously we want to write an equation for this harmonic motion. Picking out our important information. Our alpha, it's pulled down 4 inches. So our alpha is actually going to be -4 because it's pulled down 4 inches. Our amplitude is just a plain old 4, but the alpha is a -4. The 3 seconds, it says it's the time for one oscillation. That's the definition of the period. The period is equal to 2 pi over omega. We set that equal to 3 we solve for omega. We need omega for our equation, not the period or the frequency. We need omega. So again, this is pulled away from the origin or the rest position. So I'm going to use the cosine equation because at time 0 it's not at its rest position. It's pretty much that simple. If at time 0 it's not at its rest position, use the cosine equation. If at time 0 it's at its rest position, that's when you use the sine equation. So we just go ahead and plug in the -4 for our alpha, the 2 pi over 3 for our omega, and we're all set. Now, analyzing the simple harmonic motion of an object is pretty much just the opposite. They give us an equation and they want us to basically answer some questions about it. They want us to describe the motion of the object. What's the maximum displacement from the rest position? What is the time required for one oscillation? Again, this is basically asking what's the period. And then what is the frequency? Once you've got the period, you just find the reciprocal, and that's the frequency. So let's start off by describing the motion of this object. It's simple harmonic motion. Okay, that's simple enough. That's a good enough description. And then at t equals 0, the displacement is 0. So that's a good thing to include, is how far is it from the rest position at time 0. Basically, you plug 0 into the equation. So it's simple harmonic motion, and then at t equals 0, at the starting time, the displacement is 0. So this object is at its rest position at 0. That doesn't mean it's not moving, it's just at its rest position. What's the maximum displacement? Well, that's pretty easily read. I don't even really need to do any math to see this. It's our alpha. If this is negative, drop the negative, because they're basically asking what's the amplitude. So it's just the number in front. If you don't see a number in front, it's 1. What's the time required for one oscillation? Again, what's the period for this motion? So I set p equal to 2 pi over omega. Here's my omega value, so my period is 2 pi over 5. Obviously, we should reduce this if we can. This one we can't reduce. What's the frequency? Well, just flip the period, so 5 over 2 pi. Now, damped motion is a lot more real world than simple harmonic motion, because objects that are moving back and forth, whether it's the pendulum on a clock, whether it's the spring bouncing up and down, the amplitude of that motion reduces over time due to friction, due to air resistance. So that's true real world motion, when the amplitude is being reduced. Now the period and the frequency of the harmonic motion do not change. And that's actually a fact of life, and it's something that we use with pendulums on clocks, that even as the pendulum is swinging less and less, it takes the same time to swing back and forth. Now what you're going to see is y equals some function here in the front. And that function is its own separate entity that's basically reducing the amplitude with time. So we've got this function times sine of omega x, or some function cosine omega x. Again, whether it's sine or cosine depends on where it's at time equals 0. D of x, this function in front, is what we call a bounding curve. Okay, it approaches 0 and it sets the amplitude of the harmonic motion. A good example would be e to the negative x. You see e to the negative x bounding curve quite often because it approaches 0 as x gets bigger and bigger. Okay, so that's it for this lesson. It's time to get to work. I'll see you in class, and I will see you online.